Welcome back, guys. We got cut a little short last time. We were going to try and derive a function for the energy in a non-linearly or non-uniform doped semiconductor, and we got cut a little short. So I want to rederive that right now, and we're going to look at a couple things that we see in non-uniform doped semiconductors that we don't see in intrinsic or uniformly doped semiconductors, and that's the key thing we're going to be looking for is something called band bending, built-in potential, and a constant Fermi level. So where we left off last time, we have a semiconductor with some non-uniform doping, some non-zero doping gradient that increases across the semiconductor from 0 to some distance L. Okay, and it's given by this equation ND equals mx plus ND naught. And of course you can think of ND naught as being the starting position where it intersects the ND axis, and ND naught could be, NDL could be the top there. So our slope m is essentially m equals to NDL minus ND naught over L minus 0, which is just L, right? So that's another way we can look at this. Sometimes you may not be given an actual equation for doping, but if they tell you it's linear and you know the starting and the ending doping, per some distance, then you can figure it out from there. And what we're going to derive today would work for any type of doping gradient. Doping, it could be exponentially rising, exponentially decaying, linearly rising, linearly decaying, and so on and so forth. And we'll find we can derive the same things. And before we start calculating stuff, I want us to understand something conceptually, and that's the fact is that we're assuming 100% ionization in this case, and our doping is increasing linearly, so that means our electron density N is increasing linearly. So what do we know from last time? We derived this equation right here, where we see that our electron concentration N is proportional to E exponential of EF minus EI, right? And so we know that EF is equal to natural log of N over Ni KT, right, plus EI, right? EI is approximately Eg over 2, like we write that as Eg over 2. Right? So our Fermi level is actually increasing with our electron concentration, right? And but we want to write our Fermi level to be constant across the semiconductor, and we want the only things to be changing are the conduction band and the valence band. Well, how do we do that, So if we consider a constant Fermi level, and we know the expression from this equation right here, we want to say that that EI, our distance from EF to EI, is increasing as we go across, and therefore our distance from EC to EF is decreasing as you go across. We're becoming more and more N-type as we go towards L. This is L right here, right? This is what our conduction band Fermi level, intrinsic Fermi level, and our valence band should look like. It should look like something like this. This is obviously not completely scale. This is going from 0 to L. And then this is EG. Our conduction band and valence band are always separated by the band gap EG. So this is what we want to derive mathematically, right? And this is what we know it's going to look like. And we don't know the exact value of EV or EC. That's not something we can figure out mathematically, right? But we can set them a reference. We can normalize them to some value and then derive it. Because we don't know the energy, an exact energy and momentum of an electron at any time. In quantum mechanics, but we can find these delta E's, right? And that's where EG comes into play. So what I can say, erase this, I'm going to normalize EV at x equals L is going to be normalized to 0 electron volts, right? And I'm going to say EC is just EV plus EG, right? And similarly, EI is equal to EV plus 1/2 EG, right? But we want to prove this this relationship mathematically. We want to prove that that curve is true mathematically, right? So let me write these guys over here, right? EV of x equal to 0 is equal to 0. I'm sorry, x equal to L, my bad. And EC equals EV plus EG. And EI is equal to EV plus 1/2 EG. This should make sense conceptually, right? And now we're going to get into doing the math now. So, where can we start here? This semiconductor isn't connected to anything. So by Kirchhoff's law, the net current through it should be 0, right? But there is a diffusion and a drift current, just as we discussed before, right? Electrons will diffuse left, which means diffusion current is going right. And then again, once they build up over here and you get an internal electric field, those electrons will start to drift right. And so our drift current is going this way, right? The current always goes, electron current always goes in the opposite direction the electron's traveling, right? So let's start with our current equation, right? We know that Jn is equal to 0, which is equal to the charge En mu sub n dn over dx. Oh, my bad. It's not true. E, electric field, right? Plus E sub n, or diffusivity, dn over dx. So this is our gradient, this is our diffusivity, electric field, mobility, and diffusivity are directly related by the Einstein relation, which we have up here, right? Now, here's the thing. We know from this relationship here, right, from electromagnetics, we know that del V equals the negative of the electric field, right? And we know that the potential of an electron is always opposite of its kinetic energy. That means so the negative of the voltage of the potential is the positive of the kinetic energy, right? So that means if dphi over dx equals negative E, right? And we know that anytime we have a potential, energy is equal to 1 over the charge, E, times your potential, right? So let's write this in terms of our kinetic energy, right? So the electric field in terms of kinetic energy is just 1 over the charge E, dE, E is our kinetic energy, over dx, right? So I made this term positive, and it became kinetic energy, and then kinetic energy, but I have to also divide both sides by Q, or I divide this by Q to go from potential to mean energy, right? Because voltage, that's the difference between voltage and energy in terms of electron volts. So I'm going to rewrite this equation right over here in black. Electric field, E, is equal to 1 over E, dE over dx. So if we can find what E is, you know, we can integrate both sides with respect to dx, and we're going to find a value for energy, right? And then we're going to find some boundary conditions to make that, to get an actual value for that, right? Now I'm doing this all in general case, no numbers. That way you can plug this into a program and you can see for yourself, you know, what these actually look like, and you can change a couple different things, you know, for different values, and I'll show that at the end. Okay, so I'll solve for E, right? So that's just E is equal to negative E dn over dx, right? Times 1 over E n mu sub n. Oh, that's it. Okay, so E's cancel out. Okay, what is dn over dx? It's just m, right? What is d sub n? Well, according to the Einstein relation, it's just mu kt over E. Mu sub n kt over E, so that mu sub n cancels out, right? And what is n? Well, n is just our equation, mx plus n d naught, right? And then we have a kt because we use this term, so we have a kt, right? What else? Oh, what's dn over dx? dn over dx is the slope of this line. It's our gradient, right? Because we're saying 100% ionization, which means n is equal to nv of x, everything. So that's just m. Okay, so now we have a equation for E, and then using this right here, which tells us that energy is equal to, when we solve, we do, we move this dx and E over here, it's E, the integral of electric field dx, right? Let's move over here. So that means E of x is equal to negative E m k t, right? Because k, t, and m are all constants, right? And the integral 1 over mx plus nd naught, right? Sorry guys. dx, right? So how do I integrate this? I do a simple u substitution. I let u equal to, or mu equal to mx plus nd naught, d mu equals to m dx. I bring my m over and I rewrite it and they cancel out and I get equal to negative e kt, right? Come on. Oh, just checking something. ekt, natural log of mx plus nd naught plus c, right? That should be a very simple calculus problem. You should hopefully you know how to do u substitutions. So we have that, but now we have this constant c, right? So what do we have for boundary conditions? Let's see here. Oh yeah, we made a reference where EV of XL is equal to 0. So let's do this, let's let E equal EV, right? So E is now EV, right? That's just something that we're calling it, because we don't know exactly where these energy levels are. We just know the difference between conduction band and valence band. So we can set these equal to anything we want. But we're going to say E equal to EV at x equal to L is equal to 0, right? It's coming down. We're saying that this right here is at 0. Okay, this is energy and this is x, right? And that's equal to negative E kt natural log of ln of ml plus nd naught plus c equals 0. So what does c equal? C is equal to E kt natural log ml plus nd naught. Okay, so now we have an equation for EV. I'll erase this. So what is our new EV? Well, our EV, our valence band energy as a function of x, is equal to negative kt, EKT, my bad, negative EKT natural log mx plus nd naught minus EKT natural log of ml plus nd naught. How can we rewrite that? Make it more simple. E of V, valence band energy, is equal to EKT natural log ml plus nd naught over mx plus nd naught. Okay, so here's what we should ask ourselves, just as a little sanity check. What's happening as x is increasing in this term? X is in the denominator here, so EV should be decreasing as x is increasing. All right, well that looks like it follows with what generally we want right now. So what is what is EC? Well, EC is just EV plus EG. So it's just this term plus another EG. So wherever it is here, it's going to be here, separated by this band gap. All right. Okay. What is EI? EI. We're assuming the approximation where our intrinsic energy level is approximately halfway up the band gap from the valence band, right? That's something we derived last time. So EV plus 1/2 EG. Okay, I'm just writing the same thing twice. Okay. Okay, so we have our energy levels, and they do indeed follow this relationship. But now we got to derive the Fermi energy. We know that we know physically from what we looked at before that the Fermi energy should be flat all the way across. It should be constant. You know, we're kind of in a way we're writing our energy bands with respect to the Fermi energy. Okay, so how do we do that? And we can only do this because we assume that it's non-degenerate and it's a 100% ionization. So we can say that ND is equal to N, which is equal to, well, what's ND? Mx plus ND naught, which is equal to NC e to the EF minus EC over KT, right? So we're going to solve for EF. EF is equal to KT, do the algebra, natural log of Mx plus ND naught over NC plus EC. Now you're thinking, well, wait a minute, we got a problem here. Now we have EF as a function of x, so that means it's changing over distance. Well, that can't be right. Well, let's keep simplifying. Let's plug in EC and see what happens, right? What is EC? So what did we write it again? We're going to write KT natural log Mx plus ND naught over NC, right? Plus natural log EC is just this plus EG. Well, KT. Guys, you know I made a mistake here. This E right here, this charge, it actually was supposed to cancel out somewhere. I don't know where, but it's supposed to cancel out. So that E should not be there. Definitely not. So remember, see where it canceled out. So yeah, maybe you can go through that on your own. Oh, you know what? It cancels out when we use this substitution right here. All right. It was supposed to cancel out then when we changed D to D equal to mu KT over E, and our integral was E dx. This term was then right here, and the E's were supposed to cancel out. So I apologize for that. But we don't have time to redo that. So so plus KT natural log. Right? EC is EV plus EG, so ML plus ND naught, ML plus ND naught over MX plus ND naught, right? Plus EG. Can we simplify this? Yeah, we can. We have two natural logs, and we can put them together, and we can multiply the arguments together and make it into one natural log. So what do we get here? EF is equal to natural log. Oops. KT, natural log. Uh-oh. We put these two together, then that cancels out. I get ML plus ND naught over NC plus EG. Okay, let's do a sanity check here, right? ND naught is our constant doping. NC is our effective density states in the conduction band. Okay, EG is band gap. So if we have some term plus EG, but we know physically that that if this term is positive, then we have a Fermi energy that's above the conduction band, right? And that can be considered degenerate doping. But we assume that there's no degenerate doping, right? So we assume, and let's say for silicon is NC is something on the order of 10 to the 19 centimeters -3, and ML plus ND naught is, we assume if it's not degenerate 100% ionization, then ML plus ND naught is less than the conduction, the effective density states the conduction band everywhere in the semiconductor. So in everywhere in the semiconductor, ML plus ND naught is less than NC. So that means if this is bigger than this, and it's a natural log, then this whole term is going to be a negative. So the whole thing is going to be under that. And we can see it's a constant, there's no x. So what you can do, you can go home, you can plug this and this and this and this and this, or these three and that into MATLAB, and you can get a curve that's going to look just like this up here, right? So I'm going to write that equation, and we're going to derive one more thing. The EF is equal to KT natural log ML plus ND naught over NC plus EG. All right, and these are our derived equations, right? So this works for any linearly doped non-uniform semiconductor. These equations will hold, given that it has some equation like this. And you could derive the same thing, like I said, if this were exponentially growing, or if it were, saturated, like if it was a square root term or something like that. You could use the same process and find out your energy band. So we have one more unique thing we're going to look at, and then we're going to stop with this, and we're not going to talk about, we're going to get more into current transport. We notice that there's this, if positive charge is over here and negative charge is over here, we have this built-in electric field. And these changes from here to here, we have, we have an EC of 0 minus EV, or EC, EC of 0 minus EC of L, right? And the same with those, equals to some built-in potential V, right? VBI, right? Because we have a large, conduction band energy is much higher here compared to here, so that means that there's some built-in potential in this, right? So which means there's some built-in electric field that exists. So we want to figure out what that is, and what we can do to figure out our built-in potential, VBI, we can go back to this term right here, which is dV over dx is equal to negative V, right? And we can do basically what we did before, but we're going to integrate from 0 to L to find our total VBI, right? 1 over E VBI, right? So that means that VBI is equal to E of x dx from 0 to L, negative. So what is that? That is the integral from 0 to L of KTM, right? 1 over mx plus n d naught dx, right? Am I missing anything there? No, this is what we derived last time from this term right here. We set Jn equal to 0, we solve for E. We solve for dn using this up here. Our e's canceled out, and we just have this right here. Well, in this case, actually, I don't know what the hell, I'll just derive it again, So using this equation right here and setting it equal to 0, E is equal to negative E dn over dx, which is just m, times 1 over E n mu sub n, right? Dn is equal to this right here, right? So then my e's cancel out, and dn over dx is just m, the slope, the gradient, and then n is just our doping function, and so this whole thing becomes kt over e times n, 1 over mx plus n d naught. Right? That's our e, right? And it's negative, right? So we plug that into here. Gonna kind of work backwards. Plug that in here. Negative negative becomes a positive. So this becomes ktm over e 1 over mx plus n d naught dx from 0 to L. This will give us our built-in potential across the entire semiconductor from 0 to L with this non-uniform doping. All right, same thing as before. Kt m over Kt m over E, and that's 1 over, do a U substitution again here. M's cancel out, and I guess natural log of mx plus n d naught from 0 to L. What does that give me? Kt over E. After some simplification, it just gives me ml plus n d naught over n d naught. Okay. And that's what we get from that term. And so this is our built-in potential VBI. You'll notice ml plus nd naught is, that looks like that is larger than nd naught, so this is a positive built-in potential. I'm not sure if that's right, so, but let's look here. Oh yeah, that should be right actually, because if you think about it, electric field is negative of the potential. Our electric field is pointing in the negative direction, so our potential is positive, right? So I'm just going to rewrite this. So based off this equation, this one, this one, we get this energy band diagram where this is EC, this is EF, this is EI, and this is EV, and this distance here is VBI. And another way to look at VBI is it's equal to EI 0 minus EI at L, just like that. Or it could be EC is 0 minus EI at L. It could be EV is 0 minus EI, or minus EV of L. Sorry. But yeah, it's the difference between these two. So this is a really important example. It's not seen too much in textbooks. We assumed a linear doping, and we derived the values for what we see here as band bending. And band bending leads to a built-in potential, built-in electric field, and you know, due to this doping gradient. And this will be really important for when we get into depletion regions, which occur in pn-junctions and other stuff like that. But that's all we got for now. Tune in. We're going to be getting more into carrier transport and talking about mobility and the continuity equation next. So thanks for tuning in.